Hi Physics World of YouTube, my name is Alexis O'Connell, and today for my discussion we're going to be talking about Newton's second law. And today it's not an equilibrium. We have an acceleration, and we're going to discuss in what case that can happen. So here we have a man in an elevator, and we are given his mass, 72.2 kilograms. And we're asked to draw a free body diagram for the scale, and because he's standing on a scale right now. And then we're asked to find his apparent weight, which is what the scale reads when he is stationary, when he's moving upward, and when he's accelerating. So right now we're going to draw a free body diagram. So we know that we can say that our little Albert Einstein here is the circle, and we have a negative force straight down, which is mg, and that is the negative y direction because we're calling it that, and this is the positive y direction because we're calling it that. We can decide what direction our forces are in just because we want to. It doesn't really matter. And so because we have a negative mg and he's standing on a scale right here, the normal force is going to be perpendicular to where he's standing. So we have Fn there in the positive y direction. So that is our free body diagram. Do we have any forces in the x direction? No. So we know that when he's stationary, there are no forces pulling up or down on him, and there are no forces pulling side to side on him. So F net in the x is 0, and he doesn't have any acceleration in the y direction. So we can find what his scale reading is when he's stationary. We know that his real F net in the y is 0. His actual total force. But his scale reading is something different than that, and that is called apparent weight. So we know that F net in the x is 0, and F net in the y is, we have our normal force, and we have our negative mg, because it's in the negative y direction, so that's why we put the minus here, is equal to mass times acceleration. So we have to do this because he is accelerating. Even if he has a negative acceleration, we're going to account for that. But we have to know that F net is ma, and that is what Newton's second law is. F net equals ma. So because we're asked to find the scale reading of the cab when stationary, we have to find the normal force, because we're not given the normal force. We're given mass and we know gravity. So we have to find the normal force because the normal force is actually his apparent weight. So it's what he feels like he actually weighs and what the scale feels he weighs. So we can solve for Fn by putting mg on the side, adding mg to both sides, and then we have ma plus mg, and then we can simplify by taking out the m. So you know that the normal force is equal to mass times acceleration plus gravity. However, if he is stationary, acceleration is going to equal 0. And that means that you substitute 0 for a. So we're going to say that an F net does not equal 0 on the scale, but F net would equal 0 in real life. So if we substitute 0 for a, and we plug in the values here and type in the calculator, we know that his weight is Fg. And if he's stationary, he's going to equal exactly what his weight is. And that is what we're given, 72.2 kilograms times gravity. However, if his acceleration is not 0 and he's not stationary and he actually is moving, but he's moving at a velocity that is constant, if v equals 0.50 meters per second and it's constant, there's no changing acceleration, and there's a 0 acceleration, then it's the same thing. A is equal to 0, and it's the exact same problem. Remember that the scale reading is the apparent weight relative to the Earth, not relative to the elevator. Because if it was relative to the elevator, then F net would be 0 because the elevator is also moving in the same direction. However, if he was accelerating and if acceleration was not 0 in up or down, we can account for that. We already know this formula, F net in the y is equal to the apparent weight, normal force, which is also equal to the scale reading. And Fn is equal to mass times gravity plus acceleration. And we are given that acceleration that he's traveling in, so mass times gravity plus acceleration, plug that in the calculator. So that's when he's moving in the positive y direction. If he's moving in the negative y direction, you have to account for that and say negative a. So mass times gravity plus negative a is equal to this. And that is our conclusion of our lesson of Newton's second law.